So hello guys, today we are going to discuss this problem, counting bits. Um, this I have seen this problem in the Google interview, and they wanted to ask about the different approaches. So let's discuss this problem. This is marked as easy, but this is a very interesting problem. So let's see what it says. Given an integer n, return an array answer of length n plus 1 such that each I of answer I is number of ones in the binary representation of 1. So for example, if we have 2, so we have to find all the ones on bits from 0, 1 and 2. So on bits in 0 is 0, on bits in 1 and 1 is 1, on bits in 2 is 1. So the answer is 0, 0, 1. Similarly for 5, we have to go from 0 till 5 and we'll create a array of 6, right? So the 0 will have representation 0, 1 will have 1, 2 0 has 1 0, so there is only one on bit, so that's why it's 1. In 3, the binary representation is 1 1, so there are 2 on bits, and similarly for 4 and 5, 1 and 2. So there can be different approaches to solve this problem, and the follow-up is it is very easy to come up with O of n log n can you do in linear time on and possibly single pass, right? Can you do it? You can you do it without using built-in? So there is a built-in function as built-in pop count in C++ which can provide the number of bits in a number. So let's see what are the different approaches available with us. So the first approach, let us take the number 6. So first approach is approach 1 is the divide approach. So for example, for 6, what we can do, we can divide it by 2, right? So when we divide it by 2, the remainder is 0 and the quotient is 3. Then we'll note down uh, 3 here. So 3 becomes the dividend and the remainder will be 1 and quotient will be 1. And finally, for we'll take this 1 here again, and this is 3, the quotient is taken here, and we'll divide it by 0 and it is 0 and remainder becomes 1, right? So we are going to solve it until the quotient is 0 and we are going to note the reverse order. So in the reverse order we have 1 1 and 0. So our answer for representation of 6 is 110, right? So this is for the one number, and the time complexity to calculate uh, this binary representation is O of log n. How of log n? Because in every step, that is in every divide, we are jumping half of the number. And we remember that in a binary tree, if you have a binary tree, something like this the search complexity in a binary tree is log n because we jump into the half of the binary tree. So all these, when we jump on the left, all these nodes on the right are bypassed, that is skipped. Then we find that whether the number is greater or smaller than this. If it is smaller than this, then we jump here, and then again all these numbers are gone. So in this case, for finding one number, it is log n, but we have n numbers, so it will be n log n. And that question says that we should not find in n log n, we should find in less than that. So this is the approach 1. So let me go to approach 2. Okay, so the approach 2 can be the bitwise manipulation, right? So for example, we are given a number 6 and we have to find all the binary on bits in 0, 1, 2, 3, 4 and 5. 0, 1, 2, 3, 4 and 5, right? So for finding the number of on bits in 5 or maybe for any other number, let's say we want to find in 4, how we are going to do it? 4 is represented by 1 0 0. So On a 32-bit system, it will be represented something like 1, 2, 3, 4, 1, 2, 3, 4, right? So this becomes 8 bits. And since it's 32 bits, we are going for 1, 2, 3, 4 and 1, 2, 3, 4, right? So this is a 32-bit representation of 4. We will take number 1, right, whose bitwise representation will be very same, just 1 at end. So 1 here, right? So that's, yeah, okay. So now what we'll do is we'll perform a AND operation, right? So and we'll shift. So when we do a AND operation, we'll have so in AND 0 0 becomes 0, 1 0 becomes 0. So this output will be 0, right? We will then perform a left shift operation on 1. So on left shift, we will shift this 1 here and 0 will come here. It means left shift means this bit goes out, and when this bit goes out, a 0 is filled in place. So again we'll do AND, we'll find 0. We'll again do a left shift, this goes out, 0 is filled here. And in this case, and now 1 1 becomes 1. So we know the number becomes 100. So we find that this is 4 and the number of on bits is 1. Rather, number of on bits is only 1. So what is the time complexity of this algorithm? For every bit, we have to shift this one 32 times. So there are n numbers multiplied by 32 shifts, right? So we can say this is O of 32n, right? We can do this, but let's see the other approaches as well. So let's move on to the third approach. Approach 3. Approach 3 is Hamming code. So I have already made a video on Hamming code. In Hamming code, we only jump from on bits to on bits. So for example, 6 has 1, 1, 0. So the time complexity for calculating the on bits in 6 is 2. So the overall time complexity will be O of n multiplied by maximum on bits in number, right? So I have already made a video. I'll just share the link for the Hamming code. So we'll go on to our approach number 4, right, which is the dynamic programming. So in this approach, what we are going to do is we are going to analyze the property of number of on bits, right? So let's see, we have 1, 2, 3, 4, 5, 6. Let me write that down quickly. 7, 8, 9, 10, and 11 till there, right? So this is represented by 0, this is represented by 1, rather 0 1, this is represented by 1 0, this is represented by 1 1, this is represented by 1 0 0, 1 0 1, 1 1 0, all ones, this is represented by 1 0 0, then this is represented by 1 0 0 1, 1 0 1 0, and this is represented by 1 0 1 1. Okay, so the property says that the number of bits in 0 will always be 0. This is fixed. Number of bits in number of on bits in, so this is, I'll say, on bits. Number of on bits in 1 is always 1. This is also fixed. And number of on bits in any power of 2 is always 1. So we can see here 2 is power of 2, that is 2 raised to power 1. Then 4 is power of 2, the number of on bits is 1. Then 8 is power of 2, number of on bits is 1. So we can quickly say that number of on bits will be always 1 here. So what left? So now the number of on bits in 3 will be equal to, so how we can write 3 is equal to 2 plus 1. So that is number of on bits in 2, which is 1, plus number of on bits in 1, which is 1. So it becomes 2. right? So number of on bits in 2 is number of on bits in 2 is 1, number of on bits in 1 is 1, right? So for 4 we'll have 1. So for 5, how we can write it? We have number of on bits 5 is equal to 4 plus 1. So now the thing to note here is we have to go to immediate power of 2. That is power of 2 was 2 also, but we have to go to the nearest power of 2, one that happened before. So this is 4. So number of on bits in 4 is equal to 1. Number of on bits in 1 is 1. So number of on bits in 5 is 2. Similarly, for 6 we can write 6 is equal to 4 plus 2. So it will be equal to 1 plus number of on bits in 2 is again 1. So number of on bits is 2. For 7, we have 7 can be written as 4 plus 3. So number of on bits in 4 is equal to 1 plus number of on bits in 3 were 2. So total number of on bits is 3. So 1, 2, 3. That's fine. And then for 9, how we can write 9 is equal to 8 plus 1. So number of on bits in 8, which is 1, plus number of on bits in 1, which is 1. So it becomes 2. So 10 is equal to 8 plus 2, which is equal to number of on bits in 8, which is 1, number of on bits in 2, which is 1. So it becomes 2. And similarly for 11, last number I'll do, number of on bits in 8 plus number of on bits in 3, which will be equal to 1 plus number of on bits were 2, so it becomes 3, right? So in 8 we have only one on bit, and in 3 we have two on bits, so total number of on bits becomes 3. So this is the way. So the time complexity of this algorithm. So the time complexity of this algorithm is O of n. How? Because if we have, let's suppose, 11 numbers whose on bits we need to calculate, we know for 0 and 1, and if it is a power of 2, right, we will simply do it 1, and from power of 2 we are going to calculate all the numbers. So we are not going inside the number, we are just looking at the number, checking whether it's power of 2, and then finding it. Again, find how a computer or the language finds that it is a power of 2, that may again have some time complexity, but we are not bothered about it. So let's go to the code. So we have taken a array. I'll be explaining C++. We have taken an array of size n plus 1. Initially, if this is 0, we'll return the same array. Otherwise, we'll set it to 1. And we have the present power of 2 and we have the next power of 2, two variables. And we'll start from I equal to 2. So if I is equal to next, that is, it is a power of 2. So we are simply setting our dp as 1, and we are making next to the next power of 2. Otherwise, what we are doing here is we are making, let me open up this for better explanation. Okay, so if we are not a power of 2, right? I is not equal to next in this case. So what we are doing is we are doing the array. This is the dp array. dp of I minus present. So present, let's suppose I is 5 and present is 4, right? So what we are doing is dp of 1 plus dp of 4. So present is 4 and 1 is, that is 5 minus 4. And similarly, we are going to fill this. So this will, we can say this is a dp array, right? So this is pretty simple. Present actually points to the present power of 2, and next points to the next power of 2. And this is how we are going to solve it. So one more interesting thing I'll show you. So I have solved this question in, so these are from the older algorithms. So from here, I have solved in C++, Python, Rust, Go, and C. So if we see here, C++ takes 6 milliseconds exactly for the same algorithm. Python, if we see the Python code, it's again the same algorithm. The DP array is taken, then it's iterated from 2 to n plus 1, and then the same formula. And if I look at the Rust code, it's also the same algorithm. Where is Rust? right? We are iterating from 2 to n plus 1, and we are taking a DP array. So in Rust, vector is vec, and so on. So the interesting thing to note here is the Rust actually takes least amount of time and least amount of memory from the different languages. Then Go has 1 millisecond more and more memory. So I'll be discussing that why Rust takes so much less time as compared to other programming languages, even more than less than C, right? And also than C++. So definitely that's why, because many companies are moving to Rust. So yeah, that's it for this video. Thanks a lot. Have a good day. Bye bye.